This year, Rutgers University is being represented at Spaceport America 2021 by RRPL, the Rutgers Rocket Propulsion Laboratory. We're a student-led subsidiary of Rutgers' AIAA organization and teach our diverse set of members how to design, manufacture, and launch rockets. Our vehicle this year is the Eagle II V4, named after the lunar module of Apollo 11. It is the second largest two-stage launch platform that RRPL has designed and is set apart from the competition in many ways, including our use of additive manufacturing techniques. We've made our mark at Spaceport before, competing on behalf of Rutgers at Spaceport 2018 and 2019 in the 10 and 30K COTS categories, respectively. Since then, we've been pushing the boundaries, launching higher flying and more complex rockets. The responsibilities for designing Eagle II V4 are divided between our sub-teams, each of which focuses on a specific system of the overall design. This allows our teams to specialize and develop our subsystems more robustly, though we're all coming together to produce RRPL's most advanced rocket yet. Our nose cone houses most of the SRAD electronics aboard our sustainer. Eaglebrain, as it is known, is our closed-loop telemetry system that is responsible for gathering in-flight data and transmitting it to the ground in conjunction with our COTS hardware.
Eaglebrain's sensor suite collects GPS position and altitude, barometric pressure and temperature, 3-axis linear acceleration, as well as the voltage and current of the power supply. These sensors are managed by a microcontroller, inlaid in a custom PCB, which transmits the data via serial communication to a Raspberry Pi. The Pi acts as the heart of Eaglebrain, collecting and storing the sensor data. It simultaneously sends this data to our transceiver, which transmits to a receiver on the ground. The Pi also records and stores video from our onboard camera. On the ground, incoming data packets are validated and displayed on a GUI in real time. They are also logged for GPS range finding and redundancy.
We manufactured the structural housings for the system by 3D printing, which allowed us to easily design around the tapering profile of the nose cone, as well as the all-thread superstructure that compresses the nose cone tip and bottom bulkhead onto the nose cone itself. We machined this 3/4 inch bulkhead from aluminum to ensure structural integrity during drogue deployment. Additionally, this lets us include a switch on the bottom of the bulkhead so that the system can be activated externally, which allows us to arm our electronics fairly late in the final assembly. This guarantees maximum system uptime during flight and recovery. Our DigiKey transceivers are rated up to at least 100,000 feet line of sight, which is near the maximum allowable resolution of our pressure sensor. This system has been tested previously on several flights up to a maximum 15,000 feet on both single and two-stage vehicles. Eaglebrain is an example in how SRAD systems can reinforce or supplant commercial systems, allowing for purpose-built devices that fit a specific mission's parameters more robustly.
The recovery team is responsible for data acquisition, tracking, parachute design and manufacture, parachute deployment, and landing dispersion analysis. Our design approach is to thoroughly research existing solutions to these engineering problems and to determine whether we want to design a new system from the ground up or to integrate existing technologies. This allows us to quickly solve problems and elaborate from that to create custom-tailored solutions for our rocket. Guiding all decisions is an overall view of how the rocket operates so that we not only assure a safe descent, but to optimize weight, location of mass, and overall length of the subsystem to make the rocket as efficient on ascent as well.
All of the functions for recovery are controlled by 2 avionics bays, one in the sustainer and one in the booster. We designed the avionics bays around custom 3D printed sleds to assist in wire management and ease of construction and integration. CNC'd 3/4 inch aluminum bulkheads are used to seal the bays and act as the anchors for the parachutes via U-bolts and I-bolts. The sustainer avionics bay utilizes the Raven and RNC3 to control parachute deployment via ignition of black powder charges, and a Telemega is utilized to control sustainer ignition and tracking.
Our booster avionics bay takes advantage of the 6-inch diameter of the Aerobody. Here we lay flat the altimeters and GPS to reduce the overall length utilized. 2 RRC3s are used for parachute deployment and a MissileWorks GPS for tracking. Additionally, we limit the points of separation and push mass further forward by locating the avionics bay directly beneath the interstage and utilizing single bay dual deployment with 2 tender descenders linked in series. This simplifies the design of the booster and reduces the overall size of the fins required for stability.
The parachute design process begins with a custom MATLAB applet that we constructed to help facilitate ideas into an actual parachute model. Sliders on the applet allow us to adjust nominal and spill hole diameters, shape, number of gores, and seam width. When we are content with a design that fits the appropriate descent velocity, we can export the 2D drawing file as a DXF, where a CNC machine can cut out our gore on a wood template where the actual parachute manufacture process begins.
For parachute material, we use OtterTech's 200 denier ripstop nylon and N66 bonded nylon thread to make all our stitches. We cut out our gores using soldering irons, and we sew them together by the same standards that parachute manufacturers use. We use a flat felled seam and ensure that an appropriate 8 stitches per inch is being used. All edges are then hemmed and excess thread is cauterized to prevent any stitches from becoming undone. For attaching the shroud lines to the parachute, we use 1/2-inch nylon belts as shroud line attachments. Since 2020, our recovery team has made 3 custom parachutes, which include one 80-inch toroidal main, 2 hemispherical chutes that are 50 inches and 35 inches in diameter. All of these chutes have been in use and have successfully brought down our rocket at a safe descent velocity. We test each of our parachutes vigorously the old-fashioned way by attaching the parachute to a load cell and an ESP to the back of the car. A Python program allows us to collect data on the go and plot the results. As parachutes are the very core of a recovery system, we plan to do more intensive testing as well as to improve our current methods.
In an effort to minimize unknowns in the rocket's flight, we perform a 6-degree of freedom Monte Carlo simulation to obtain landing dispersions up to 3 sigma standard deviations from the mean landing coordinate. Anticipating the landing zone of the rocket is essential to determine the safe operation of the vehicle and benefits recovery's efforts for retrieval.
The Aerobody team designs the overall airframe of the vehicle as well as components needed for stable flight. We are also responsible for the construction of the rocket, including the launch rail systems. The team's design focuses on modularity, and as such, the entirety of the launch vehicle can be disassembled or reused for similar flights multiple times over. The modular fin can and boat tail design allows us to easily switch out different motors and different fins with relative ease. Our use of 3D printed components allows us to quickly develop and fly parts that would otherwise take many hours of skilled labor to produce or could not be produced under traditional machining techniques.
The Rutgers Rocket Propulsion Lab team has been experimenting with and implementing additively manufactured components for aerodynamic, structural, and load-bearing purposes. The key advantages gained in this approach are easily reproducible parts, greater modularity, and reinforcement of designs that could not be incorporated under traditional manufacturing techniques.
Our interstage and fin can brackets are load-bearing and therefore manufactured from a 3D printing filament known as Onyx. Onyx is a nylon-based material that is infused with carbon fiber strands. The interstage is designed with a cavity created from a mold of the boat tail and fin can that it's mating to, holding the 2 stages securely in place. The interstage was also made to withstand the torque placed on the rocket during launch under a certain angle, and to support this, the interstage has been reinforced with 4-threaded rods that are designed to post-tension the part. By utilizing this post-tensioning, we're able to drastically increase the strength of the 3D printed component.
By having 4 identical fin can brackets mounted around the circumference of the rocket and bolted together to hold the fins in place, each section can be easily replaced with spare parts if any particular component is broken. Comparatively, external fin cans made from a single piece of steel or aluminum will need to be completely removed and replaced if damaged. This process may not even be possible without damaging the rocket body itself, as these are often held in place with epoxy. However, with the fin can that bolts into place, both the brackets and fins can be replaced individually. This creates the ability for this area of the rocket to be reused for future flights.
The boat tail concept on the booster stage is designed to accommodate any motor up to 150 mm in diameter, while the sustainer boat tail design can house any motor up to 98 mm in diameter. On each of the boat tails, there is an internal thrust ring that mates with the motor as well. Due to the streamlined design, the boat tail is able to reduce overall parasitic drag on the rocket body.
Flyaway rail guides provide the advantage of releasing from the rocket once it has left the guide rail, reducing the overall drag on the rocket compared to a permanently mounted guide. By having the freedom afforded by 3D printing, we have been able to create flyaway rail guides made of 2 pieces that strap around the rocket using bungee cords. These 2 pieces are then able to slide down onto the rail with little room for unnecessary movement, and this allows the rocket to be held vertically. These guides keep the rocket on the launch rail, but they do not experience substantial load themselves, and given this and the complex nature of some rail designs, 3D printing was the obvious choice for the construction of these pieces. The motor bulkheads for both stages are CNC cut by our team from 3/4 inch T6061 aluminum. These bulkheads are the load-bearing components that transfer all of the thrust from the motor to the rocket body. The fins required for stability are also CNC machined from aluminum with a special guide curve that hugs the curvature of the boat tail. The CNC machine also offers us the capability to machine our fins to a tapered point.
By utilizing both 3D printing and CNC manufacturing for the development of our launch vehicle, we are able to produce a highly modular 2-stage rocket that is cost-effective and quickly reproducible.
For our next launch, RRPL hopes to send the newly designed Eagle version 5 to 48,000 feet. This launch allows Rutgers to make an even bigger mark in the field of collegiate high-powered rocketry. After this goal is achieved, we hope to keep improving on the Eagle series until reaching the Kármán line. We thank all of those who helped us, such as Rutgers, AIAA, and the NASA New Jersey Space Grant Consortium. We're so honored to be part of the Spaceport America Cup this year, and we have a lot of fun preparing for it. We've grown closer as a team to meet our goals, and we're grateful for each of our members for putting in the effort to see projects get completed. We're excited to see what the future holds, and we can't wait to attend Spaceport this year.
I did not know that there was a tradition of showing some family pictures, but this has essentially become my family over the past 2 years.